Okay, just imagine this for a second. You're a scientist, maybe years into a really groundbreaking project, and then poof, the funding just vanishes. Now, for thousands of people in the US biomedical world, this wasn't some nightmare scenario, it was their reality back in 2025. And, as the dust started to settle, a really interesting pattern began to emerge. It suggested this wasn't just some random financial shock. So let's follow the money and let's find out who really paid the price. All right, first things first, let's just get a handle on the sheer scale of what happened here. I mean, we're not talking about a simple budget trim. This was more like a financial earthquake, and the aftershocks, they were felt in labs all the way from coast to coast. So the story really kicks off with this one number, 2,291. That's how many active, ongoing research grants the National Institutes of Health, the NIH, suddenly terminated in 2025. And let's be super clear about this. These weren't new applications getting a no. These were projects that were already up and running in full swing.
And you've got to remember, behind every single one of those grants, there are teams of actual people. We're talking principal investigators, the lead scientists, postdocs, grad students. All of them had their work just stopped, dead in its tracks. Thousands of different projects, on everything from cancer research to genetics, were just thrown into complete chaos.
And the dollar amount? Whoa. It's just as staggering. The NIH pulled back $2.45 billion, with a B. And this was funding that had already been promised, already allocated. I mean, that is a massive, massive amount of money to just yank out of the US research system with basically zero warning.
Right, and this whole thing didn't happen overnight. It wasn't like ripping off a Band-Aid. No, this crisis unfolded over several really agonizing months. It started in February 2025 and just dragged on right through the summer. So you can imagine, this created this long, drawn-out period of total uncertainty for everyone. And here is where you really see the sheer waste of it all. By the time these grants got the axe, almost 52% of the money was already spent. Just think about that for a second. That's money that went to people's salaries, to really expensive lab equipment, to critical supplies, and it was all basically just thrown away because these projects were killed before they could ever produce any results. Okay, so we've established this was a massive, incredibly disruptive event. But the real story here isn't just that the cuts happened. It's where the fault lines started to show. And once you start digging into the data, it tells a fascinating and, frankly, a pretty disturbing story about who really got hit the hardest. I mean, look at this. No region was spared. You've got Harvard in the Northeast, Stanford out on the West Coast. You go down south to the University of Texas system, or to the Midwest with the University of Michigan. All these top-tier research institutions across the country felt the pain. This was, without a doubt, a truly national crisis. And this right here brings us to the most crucial question of this whole explainer. When you see an impact this widespread, it's natural to assume the pain was shared pretty evenly, right? But was it? Well, the data tells a very, very different story. So when researchers started to really dig into the demographics, who these scientists actually were that lost their funding, some really clear and honestly concerning patterns started to pop up. It turns out the burden was, it was far from equal. Okay, take a look at this chart because it's really revealing. What you're seeing here is how much money was left on the table, the unspent part of the grant, when the funding got pulled. For projects led by women, almost 58% of the money was still there. For men, about 48%. Now, that 10-point difference might not sound like a lot, but it's huge. It basically means that on average, women-led projects were cut off much, much earlier in their life cycle, which causes a way bigger disruption to their research. And the source material we're looking at really nails it. This difference in unspent money meant that, and I'm quoting here, women investigators faced greater disruption to ongoing projects and lost a larger share of unrealized scientific output. It's a huge loss of potential. And if you want a really stark example, check this out. Let's just look at one place, the University of Michigan. The median, so the typical, canceled award for a project led by a woman was over $383,000. And for men, just over $20,000. I mean, that is just an enormous, enormous difference. It really shows how wild the impact could be, even inside the very same university. But it wasn't just about gender. The dash shows us another critical fault line, and that's career stage. It turns out this whole shock was especially damaging for the people who were already the most vulnerable, scientists who were just starting out their independent careers. And this problem gets even sharper when you combine those two things. Check this out. Among assistant professors, and that's a real make or break time in a scientist's career, almost 60% of the grants that got terminated belonged to women. Think about that. Losing your main funding right at that critical stage, that can be a career-ending event, full stop. And the damage just ripples further down the scientific pipeline. When you look at the really critical training and fellowship grants, the ones specifically designed to support the next generation of scientists, women were hit harder across the board. So you see, this isn't just about hurting the researchers of today. This is about damaging the very future of science itself. So, okay, what's the broader ripple effect of just pulling all this money out of the system? Well, we can actually try to estimate the wider economic loss. And let me tell you, the numbers are pretty big. To figure that out, we use a tool called an economic multiplier. It's actually a pretty simple idea. The NIH has calculated that for every single dollar it invests in research, it ends up generating about $2.56 in other economic activity. You know, things like creating jobs, spinning off new tech, and just people spending money in their local communities. So when you do the math, you take that $2.45 billion in canceled funding and apply that multiplier, what you get is a potential unrealized economic output of almost $6.3 billion. That's the estimated value that never made it into the US economy, all because these projects were stopped in their tracks. Now, it's super important to add a little clarification here, and this comes straight from the source paper. This number is an estimated benchmark of the potential loss. Think of it as a tool to help us understand the scale of the disruption, not a super precise calculation of money that we can prove disappeared from the economy. Okay, so when we put all of these pieces together, what's the big picture? What does this all mean for the future of American science? Well, all the data we've just walked through points to a really serious systemic vulnerability. And this really lays out that chain of consequences perfectly. It starts here. Abrupt funding cuts create instability. Simple enough. Then, as we've seen, the data shows that early career researchers and women are the most vulnerable to that instability. Step 3, well, that weakens the whole scientific pipeline where these groups are most represented. And the final result? The long-term scientific leadership of the entire country is put at risk. It's a domino effect. You know, the study's authors really put a sharp point on it at the end. They say the patterns we document raise important questions about the vulnerability of early-stage investigators, training environments, and scientific workforce diversity under conditions of funding instability. It really forces us to ask some tough questions, right? Like, how do you protect the diversity of your scientific talent when the system itself is so unstable? And that really leaves us with this one last critical question to think about. The cost here isn't just about the dollars that were lost or the projects that got canceled. If our scientific system is set up in a way that the newest, most diverse talent is the first to get washed out when a storm hits, what is the true long-term cost of that instability for all of us, for discovery and for innovation?